Welcome to the Density Part 2 video podcast here at Ontario High School. We're going to be all about finding mass. Let's look at the traditional methodology for solving density problems. In algebra, you have done a lot with three variable equations, and that's what the equation for density is. The base equation is d is equal to m over v, which is density is equal to the ratio of the mass to the volume. Now, in solving three variable equations, what we would do is try to isolate the unknown variable when we know what the other two are. In this case, because we're solving for mass, we want to get it by itself on its side of the equation. So we're going to multiply both sides of the equation by volume. So we get volume times density on one side is equal to mass times volume divided by volume on the other side. The two volumes on the mass side would then cancel out, and we're left with the working equation of volume times density is equal to mass. Let's try a sample problem using the traditional method. Aluminum has a density of 2.70 grams per cubic centimeter. What is the mass of a 6.85 cubic centimeter sample of aluminum? Our first step would be to write a data table reflecting the knowns and unknowns. We don't know our mass, it's what we're trying to solve for, so we're just going to put a question mark next to the symbol for mass, m. Our volume is 6.85 cubic centimeters, so we write that down. And we know our density, it's 2.70 grams per cubic centimeter. So we've taken care of step one, we have our data table. Step two, we want to write the base equation that relates density to mass and volume. And we use that in part one. It's d, or density, is equal to mass divided by volume. Once we have our base equation, we can then rearrange the base equation to solve for the unknown variable, which is known as our working equation. So as we talked about in a previous slide, we're going to multiply both sides of the equation by v, which is the volume, so that it cancels out on the mass side of the equation, leaving mass by itself, and so we'll have the volume times the density is equal to the mass. Once we've rearranged the equation to isolate the variable we're solving for, we're then going to go ahead and do step four, which is to solve for mass using the working equation. So we're going to plug our quantities in. 6.85 cubic centimeters times 2.70 grams per cubic centimeter gives us an 18.5 gram mass. Now the number of significant figures here is 3 based on the measured quantity of 6.85 cubic centimeters. The density here is an absolutely known value, which means the number of significant figures associated with the density would be considered infinite, so we don't base the number of significant figures in our answer on what the density quantity is. We look at the measured quantity, which in this case was the volume. So the mass of 6.85 cubic centimeters of aluminum is 18.5 grams. We've talked about the traditional method, which you have practiced many times in algebra, but in chemistry we often use what's called a factor label conversion method or dimensional analysis, depending on what your textbook uses as a preferred term. Because we have been doing unit conversions with this, it's a very simple way to find out what the unknown quantity and density relationships is. So let's solve this same problem using the factor label conversion method. We have aluminum with a density of 2.70 grams per cubic centimeter. We want to find the mass of a 6.85 cubic centimeter sample of this. So the method depends on an understanding of the density equality. If I have 1 cubic centimeter of aluminum, I have 2.70 grams of aluminum. Those quantities are equal. Okay, that's the equality we're talking about, and we can do something with that. Because we know that 1 cubic centimeter of aluminum is exactly 2.70 grams of aluminum, we can write this as a conversion factor. And in fact, we can write two conversion factors from that equality. In the first, we have the mass over the unit volume, 2.70 grams over 1 cubic centimeter, or we can write it 1 cubic centimeter over 2.70 grams. These become useful to us when we go to solve for the unknown. When we solve relationships involving density using the factor label conversion method, we're first going to write down our known quantity. Then we're going to multiply by one of the conversion factors that we talked about on the previous slide that will cancel our known values unit and leave us with the unit of the quantity that we desire. So the unit that you're going to should be on top. The unit that you're coming from is on the bottom, and the next slide will show us details on how that should look. So here's how it should look. We're starting with a known value of 6.85 cubic centimeters. So we're going to choose the conversion factor that has the unit we're going to on top, which is mass, 2.70 grams. On the bottom we'll have the volume of 1 cubic centimeter, so that the cubic centimeters cancel in this exchange, and we're left with grams, which is the unit that we're looking for. So we're using the volume and the density relationship to find the mass of aluminum. Now, when we do this, you'll notice the cubic centimeters cancel. We're left with grams. The 6.85 cubic centimeters times 2.70 grams divided by 1 cubic centimeter leaves us with 18.5 grams of aluminum. The same answer is using the traditional method, but a little bit faster, quicker setup on this. It's your turn. Here are 3 problems. You're given the density and volume of a metal cube, of a liquid, and of a gas, and we'd like you to find the mass of each of these. The best way to do that is to have a calculator handy, a piece of paper to work these out on, and we'll have you pause the podcast, go ahead and work these problems, and when you come back you can look at the solutions and see how you did. Let's look at the solution for A. You are welcome on any test here at Ontario High School to use either the traditional method or the factor label conversion method. You can even use a ratio method if you choose, as long as all proper mathematical support is shown for your solution, your answers are labeled properly, and your significant figures are correct. Now, we have a volume of 216 cubic centimeters. We're going to multiply that by the density, 7.9 grams over 1 cubic centimeter. We're using the density as a conversion factor, and the answer, our cubic centimeters, will cancel. We're left with grams as a unit, and we get 1,700 grams. Now, right away you're going to notice there's a mistake here, and we need to fix that mistake because there are 3 significant figures in this answer. Now, in order to get 3 significant figures here, we need to either put a line over the 0 directly after the 7 to indicate that that 0 is significant, or we would want to put this in scientific notation and make it 1.70 times 10 to the third. Either way will correct that. But it's very important that we have the proper number of significant figures here, and I will take full responsibility for my neglect in not putting a line over that 0. So don't you make that mistake. Let's look at the solution for problem B. Here we have a liquid with a volume of 12.5 milliliters. We're going to multiply that times the density, 1.44 grams over 1 milliliter. The unit we're going to, grams, is on top. The unit we're coming from, milliliters, is on the bottom of our conversion factor. We cancel the milliliters. We're left with grams as a unit, and we get 18.0 grams for the mass of the liquid. The solution to the last of our your turn problems has to do with a gas that has a volume of 89.5 liters and a density of 1.29 grams per liter. We're going to take the volume times the density used as a conversion factor, the quantity we're going to on top, grams, and the quantity that we're coming from in the density, which is liters, is on the bottom of that conversion factor. The liters cancel. We're left with units of grams, so we know that we set our problem up correctly. 89.5 times 1.29, rounded to correct number of significant figures, would be 115 grams, and that's our solution. We've come to the end of the part 2 of the density series of podcasts here at Ontario High School. It is the end of part 2, but there are more parts to come. And I want to leave you with a favorite quote of mine from Greek philosopher Epictetus. First learn the meaning of what you say, and then speak. I wish you well.